This is Autoline This Week, the show that gets you inside the global automotive industry. Autoline This Week partnered with the Consulate General of Canada in Detroit to produce this episode.
Hi, I'm John McElroy, and welcome to Autoline This Week. Today we're going to be talking about the amazing world of simulation, more specifically what they're calling digital twins. And if you haven't heard about that yet, you're going to learn something today because I've got two experts to talk about it, including Prith Banerjee. He is the Chief Technology Officer with Ansys. We've also got Ashish Naik from National Instruments, now called NI, where he's the Group Manager for ADAS and Autonomous Validation. And thanks for both of you joining me on the show today.
Thank you. Thank you for inviting us.
Yeah, thanks for having us.
I only recently learned about digital twins. I'm sure a lot of the audience has not heard of it. Prith, give us a definition. What is a digital twin?
Yes, so thank you, John. So a digital twin is basically a virtual model of a physical asset. The physical asset can be an airplane engine, a car, a building room, an air conditioner, a chiller, a transformer, a robot, whatever. But then you have a model of that asset, and what makes a digital twin is a two-way information flow between the physical asset and the model. And so what the beauty of this is, with this digital twin model, you can not only look at the past, but you can predict what is going to happen in the future. So, for example, with an accurate digital twin model, you can predict when an aircraft engine is about to fail and thereby take corrective action.
And so, Ashish, I've heard of CAD/CAM, computer-aided design, computer-aided manufacturing. I've heard of CAE, computer-aided engineering. What's the difference between them and this new concept of a digital twin?
I think, as Prith mentioned, it's the ability really to see that real-world capability in simulation. I think those two worlds of CAD/CAM and physical world are now coming together, and that's really where the essence of the digital twin is.
And Prith, what's the technology change that's enabled you to be able to build a digital model of a physical asset?
Absolutely. And so what has happened is, people talk about the smart connected world, right? So you may have a transformer or an engine, and people are putting sensors on that asset and collecting data from that asset through IoT sensors, the world of Internet of Things. So up until a few years ago, what people used to do is to take that physical asset, collect data from the IoT sensors, and measure, right? Say, okay, this is the normal behavior of the asset. Like we human beings, right? The normal temperature that we have is 98.4. Now, before we fall sick, our temperature rises to 100, 101, 102, and it's, oops, my temperature is increasing, bad things are about to happen, and we flag that, therefore, our body is about to fall sick, and we take corrective action like taking Tylenol, right? Same thing used to happen in the physical world, right? People used to monitor assets and do data analytics-based digital twins. What we found out, and in a previous job, I used to be CTO at ABB and Schneider Electric, we used to collect a lot of these digital twins based on analytics alone. What we found is the accuracy of that data analytics is limited to about 80%, right? And now, more recently, what we have done is we have done physics-based simulation, right? Where we look at the physics of the transformer, the physics of the aircraft engine, the physics of the inverter, and we combine that with data analytics to build what is called hybrid digital twin. And so the accuracy of the prediction goes from 80% through pure data analytics to 90% with simulation and 99% with the hybrid. This is where the technology is today.
And Ashish, my understanding that the auto industry is so interested in this is reducing the time to develop a new car or any component in it. In fact, General Motors, for example, says it's taken 2 years out of its product development process. I'm not sure it's all through digital twins, but isn't that one of the real benefits of this is you can develop new products far more quickly?
Oh, it's huge. It's not only just in, I would say, the traditional automotive where we're able to release vehicles to market much faster, reduce the cost. The vehicle prototypes is a huge cost in the development process of the vehicle. But it also allows us benefits in the emerging areas of automotive. So whether that be software of the air updates and needing to kind of embrace more of a software mindset for new deployment of capability, but it's also huge in these infinite spaces and complex worlds like autonomy, where it's just impractical to deal and test and design for every circumstance in real world capability. So simulation and digital twins gives us is going to be the enabler for us to deliver that capability to market.
And Prith, is that the main advantage, is being able to develop things so much more quickly?
Absolutely. And so let me sort of add to and complement what Ashish just said. So let's look at the world of autonomous driving, right? And what's the difference between a normal human-driven car and an autonomous car? The fact is that you're removing the human driver, the sensors that the human has. We have eyes, we have ears, we listen, and based on it, we take action. In an autonomous car, you have put sensors like a LiDAR sensor or a camera sensor or a radar sensor that says, here is an object in front, and I need to stop the car. So in the world of autonomous driving, people, as you see all these different car companies driving these physical cars around, right? And today, most of these car companies have driven the car for maybe on the road, on actual driving, for about 25 million miles. It turns out that you need to drive for about 8 billion miles to do the certification that you are absolutely safe to drive this autonomous car. You can now do it through simulation, right? Essentially, with simulation, you can model, right? So you may be driving a car on the San Francisco's Golden Gate Bridge when it is 9 a.m. in the morning, when it's sunny. But through simulation, you can simulate the fact, what if it is 9 p.m. in the evening and it is snowing in San Francisco, and instead of having 2 pedestrians, you have 100 pedestrians and a cat and a dog. You can do these scenarios, right, through simulation and see if the car will actually brake in those situations, right? Now, it would, for you to get to that edge case, it would take you, as I said, 9 billion miles to get to that point. You can accelerate all of that through simulation. And this is how the simulation technology and digital twin technology is allowing automotive companies to accelerate the way we do car designs.
Ashish, I also hear these terms, software in the loop, hardware in the loop, even driver in the loop. Is that all part of digital twin, or is digital twin part of that? Explain it to me, please.
They're correlated. I mean, software in the loop, hardware in the loop, driver in the loop, these are all kind of core areas where customers and people need to do testing to enable, to make sure we've got the kind of safe functionality in the road. So software in the loop is the ability of testing pure software, typically in the cloud, typically just testing the application software, whereas hardware in the loop allows us to then combine that with real ECUs and gets us that one step closer to what the real car is. And then driver in the loop is also then adding the human element, the unknown factor to that, and actually seeing how does the driver behave in this. And there's some really interesting scenarios for that. So, watching how a driver is going to react when their car is automatically parking for them, and their behavior and their, if the vehicle is doing something that they don't expect, what are they going to react, and are they going to grab the steering wheel? We talk about autonomous driving, and a number of the scenarios talk about handovers. So where the car is actually driving itself in a particular use case, and they have to notify the driver, actually, you need to take control because we found a situation that we can't deal with. And all of these then gets us that one step closer, and this is what driver in the loop is part of.
So how do people react to that? I mean, are they able to deal with the situation in simulation as if it was the real world, or is there still a disconnect between the real world and simulation for drivers? I mean, ordinary people, not, specialists like yourselves or other engineers.
So I think it's a case of separating a little bit of that. I think the continual goal of all of our organizations is to get simulation closer and closer to the real world, so we can do more of those testings in an area that is actually under our control. Prith talked about weather and day of night. In simulation, we don't have to wait around to turn on the snow or to change the light conditions. We can control all of that. And this will also give us the coverage of testing more different types. And actually, the goal of all of our companies is to be hidden from the customer, right? Our goal is to make sure that we've got the safe cars where the consumer that's buying their autonomous vehicles they should never really need to worry about simulation. They just need to have confidence in the car that they've bought off the forecourt. And this is actually the thing that gets me and Prith excited is, I suppose, being some of the hidden companies that are making enabling this technology to get to market.
Mm-hmm. Prith, I got to believe you've got a constant feedback to this digital twin model to make it more and more accurate. You had talked about this hybrid approach too. Can you go into a little bit more detail on that?
So before I do the hybrid, let me kind of talk about how the technology of simulation has advanced in the last 50 years. So Ansys is a 50-year-old company, and we got started in the core area of physics-based simulation for structures, right? And at that time, the computers were sort of relatively wimpy computers. So you in a given amount of time, right, you could only do a certain amount of accuracy in the simulation. Now, in the real world, what people want is super accurate simulation, and it has to be super fast, right? So they can literally model it in real time. And you want it robust, and you want to ease of use. So in the last 50 years, the world of CAE, computer engineering and simulation, has advanced to the point that you can simultaneously get super accurate, super fast, super robust, and very easy to use simulation. And that has really enabled sort of customers such as NI to do all these wonderful things that we are doing. Now, there are technologies that have happened, right, in the industry, like high performance computing, right? In the past, you were limited to the wimpy processors that you had in your workstation or your laptops. Nowadays, you can have shared memory multiprocessors, message passing machine, GPUs, and so on, all the accelerators to accelerate stuff, right? So today you can simulate things so accurately on these super fast computers. The other technology you have is AI machine learning, right? Which oftentimes takes these simulations and runs it like 1,000 times faster. So we are bringing all these capabilities together in the world of digital twins. And then we have, in the area of hybrid digital twins, we have sort of done combination of data analytics-based digital twins with physics-based simulation to get people that sort of, as you call, digital twin on steroids. It's a very, very exciting area.
So how do you make sure as an engineer or somebody working on this that, I mean, you must be getting a ton of information. How do you make sure that you're focusing in on the right information and not just getting overloaded by it all? Ashish, you want to take a stab at that?
Yeah, that's a great question. I think ultimately, when we think about the different engineers that are out there, everyone's got their focus. And so if you're an autonomous driving engineer and you're focusing on all the different sensors of the vehicle, your goal is to make sure that those sensors are seeing what the world is expecting you to see. And then you're passing that information in a way to different types of engineers like machine learning and AI engineers that are then computing this to the equivalent of our brains to perceive what they expect to see so we can then make decisions on it. And so I think when you look at actually the reality of it, each engineer has a particular goal in mind that they're trying to solve. Actually, the more interesting question for me, John, is how do you make that data available to everyone so that we kind of break this one engineer working on one data set that they've created, but actually making it a much bigger data set with the right meta information and set that can be searched, it can be viewed to enable multiple engineers across an organization to look at it. I think that's probably some of the subtlety differences that we're seeing in the market. I don't know, Prith, from a simulation perspective, you create huge amounts of data. So how are you kind of finding your customers are dealing with that simulation data?
Absolutely. And what I will just add to what Ashish just talked about is, I mean, you see or you hear all this technology is called the metaverse, right? What is a metaverse? Essentially, there is a universe of the physical universe that we work about, right? And the metaverse is this alternate universe, right? Which is enabled by simulation, by things like augmented reality, virtual reality, and so on, right? So you may have a physical engine, which is the physical engine, then you overlay it through a simulation of how we think the engine will operate, and you are looking at the engine through your augmented reality glasses, but then you can do all kinds of what-if scenarios, right? What if the temperature of this engine were to be high? And what if it, so you could do all these what-if scenarios in the world of AR, VR, which is accelerating the way engineers will be designing things in the future. So we see tremendous opportunities using the sort of metaverse technologies in the future, which obviously with Microsoft and Facebook and others are working on. But we are going to enable the core technology of metaverse will be enabled through physics-based simulation.
How far can you take this? I mean, in my mind, I'm thinking of developing a new car. Prith, you've talked about aircraft and the like, but can you take it beyond, physical objects? For example, could you simulate supply chains? Could you simulate the buyer experience of a new way of selling cars to people?
You can absolutely do that. So let me answer first, and then let Ashish talk about, right? So let's look at, we talked about the world of AV, but let's look at sort of electrification, right? So in the electrification thing, you're replacing your internal combustion engine with electric motor, right? And so now you're saying, okay, I have a high-powered electric motor, which is powered by batteries and powered by sort of how do you model the battery system in a car and so on. All these what-if scenarios, and then you put the electric car in a setting which is driving on the highway in downtown Seattle, and you have connections that you're going through with sort of 5G antennas and so on. So where we are headed is we should be able to model a smart city with having millions of cars in the city. Some of them are driving EV cars, some with AV cars, enabled by 5G, enabled 6 and so on, and we can do the sort of the antenna simulation of these multiple input, multiple output MIMO antennas, right? And look at exactly whether the signal will go into this particular car at this intersection. So the world of simulation that we are here is super, super fascinating. And it is all going to be powered by these high performance computers, right? Running on the cloud. And that's kind of where the world we are headed.
Ashish, you want to add to that?
Yeah, I was just going to say, I think, John, we're already experiencing that. I think when we look in the design in the engineering studios, people are using simulation, augmented reality to design the vehicles of the future. I think we're seeing in research people using that in all sorts of ways. And I think also as consumers, right, we're also looking and designing our cars, our next vehicles, what color it should be, what engine it's going to be able to look around it. You do that all online from the comfort of wherever you are, and you're looking at computer data engineering, you're looking at essentially a virtual representation of the real world. And so I think we see all of that around us today already. And I think that the future is just going to get more and more exciting about how representative of the real world we can actually do digitally over the next coming years.
Wow, it's amazing. You're going to be able to simulate the entire real world.
I mean,
let me give you a very simple consumer example, right? I mean, when you buy a piece of furniture, right? I mean, you are looking at it on the screen and you say, well, how will this piece of furniture look when I put it in the living room, right? Now in a actual store, you have fantastic lighting and so on, right? But in your living room, you may only have yellow colored light, right? So in the future, you'll be able to shop for things and with the right lighting conditions, and you can simulate those lighting conditions to say exactly how that piece of furniture or that car or whatever thing will go in the lighting conditions. And this is the power of simulation. This is the power of the metaverse, right? And you can literally do all kinds of what-if scenarios. And in my living room, what if that light bulb fuses right on top of it, right? And I can actually simulate and see exactly how it would look. Imagine the power of how it connects to customers, right, and consumers.
Yeah, and I think just to answer your question, John, I think potentially, right, I think at the end of the day, the technology is growing so fast and is capable. It's really just the imagination that will limit us in what is possible, what we can develop against. I think and the autonomy world and the automotive world has, in some ways, the digital twin has had both a positive impact as a phrase, but also a negative, because it's created people have said, oh, but you can do this. And we've sometimes missed the business case or what is the need behind it. So for me, the encouraging thing is actually thinking about the focus of what are we actually trying to solve and what is the benefit behind it. And so, from an engineering perspective, it's obvious when we look at the digitization of like an electric motor or a autonomous vehicle, we can enable less prototype vehicles, or we can make safer autonomy vehicles. There's a pretty clear need behind the digital twin, and I think that's one of the things whenever I've been assessing digital twin capabilities or requests or needs in the market, it's really making sure we've got the focus of what is the benefit that we're actually going to gain from it, and then working towards it. Because otherwise we could end up in a situation that the technology is great, we've got great ambition, but reality is it going to get uptake? And I think that's the other thing we're all striving for, is uptake and feasibility to get autonomy and electric vehicles to market.
Mm-hmm. Where does the automotive industry stand in all this? I mean, for example, I've heard that Volvo Cars and John Deere, just two examples of two companies, are demanding that their suppliers only supply them or work with them in terms of digital twins. I'm just curious, based on what you all know, where does the automotive industry stand in the use of digital twins?
So let me address it first, and then we'll have Ashish talk about it. So we at Ansys are working with all the top automotive companies, the OEMs and the suppliers. And where the world is headed is essentially, as you said, the OEMs are requiring the suppliers to provide the right model, digital twin models of the supplied components and so on. And this is essentially where the world is headed, both in the automotive and aerospace and in sort of the trucking industries and so on.
Mm-hmm.
And I think it's going at different paces. I think the automotive industry has typically been a very mechanical industry, which has moved to kind of electronics and software and systems. And I think in the traditional domains, it's had a pretty big uptake actually to embrace simulation. And I think, though, looking at some of the newer emerging industries, especially in like EV and autonomy, the people that they're hiring into the automotive industry are coming from simulation backgrounds, from software backgrounds, from non-traditional automotive, and they're much more versed in the need for simulation and are really kind of driving change in the industry. And so I think we're all at the uptake. For me, it has been pretty dramatic, especially in the last 18 months, to kind of see a big change in embracing simulation, in actually just embracing new mechanisms and new methodologies because of the ever kind of competing industry and complexity that they're faced in the automotive industry. And so for me personally, I think it's incredibly exciting. It's probably one of the biggest changes I've seen in the industry. And yeah, I think the uptake of new methodologies, including simulation, is somewhat here to stay.
So where's the auto industry right now in terms of what it needs to do? It needs to develop better twin models? Does it need to just deploy this throughout its organization? Does it need to tap into its own creativity and figure out what's next to be able to simulate? Where do y'all think we stand right now?
For me, a big area. Go on, Prith.
So in the past, right, when you owned a car, you did preventive maintenance on your car. You had to take your car and get the tires rotated every 5,000 miles, right? Or do your engine oil change every 15,000 miles, right? Who makes this decision of this 15,000 miles or 5,000 miles? That's based on hundreds of millions of cars and drivers and so on and so forth, right? Now, Ashish is a very safe driver, I know that for a fact, right? So, and he doesn't accelerate and brake as fast as I do. So for my car, I would need to do an oil change every 2,000 miles, and Ashish can do it every 15,000 miles. However, this generic thing of, change your oil every 15,000 miles is done based on statistically across all 100 million drivers in the world. Where we are headed is through the world of IoT and sensors, right? The car companies will be able to predict, exactly measure what is Prith's driving behavior, what is John's driving behavior, what is Ashish's driving behavior, and provide the right maintenance exactly when you need it, right? You should go and change your oil after 2,748 miles, and Ashish will do it after 13,020. And why is that? Because there is cost that is wasted, right? They change the oil before they needed to change the oil, or they change the oil too late and the engine bursts, right? So essentially what is happening is people will go towards much more accurate predictive maintenance, right? It will replace the oil, rotate the tire when you need it, not in a generic way. This is where the industry is headed.
Mm-hmm.
Yeah, I think the industry is also in a state where it is changing. I think the supply chain is changing. I think the key to digitization and simulation is collaboration through the supply chain. I think that there's definitely what we're seeing is the car makers, the automakers are asking more of their suppliers. There's gone are the days, I think, of creating a requirements document, throwing it over the fence, and waiting for a supplier to create something and deliver it back to them. But there's a huge amount more emphasis on collaboration, sharing data sets, sharing models, and sharing information to accelerate the vehicle to market with improved quality and at lower cost.
Mm-hmm. So, Prith, we're down to the very end here, but so I'll need a quick answer. But it sounds like this is growing by leaps and bounds, this whole concept of digital twins.
It is actually the digital twin market, according to projections, is going to be a $26 billion market by the year 2025 across all verticals. But automotive is one of the most exciting verticals in that area. And that's why we at Ansys are super excited about digital twins.
And why automotive? Why so excited about that?
I mean, digital twins are applied in sort of in aerospace industries, automotive industries, and manufacturing and others. But the automotive industry in general, right? It's sort of looking to, that the example, the preventive maintenance that I talked about, right? The opportunity to do much more accurate analytics, right? That check brake engine light on that comes out on your car, right? Imagine if you could do, if that light came on exactly when it needs to, right? Not before, not after, right? And this is where the automotive industry is so excitingly sort of headed to really leverage the power of digital twins.
Well, it's going to be fun watching this all develop. So Prith, Ashish, thanks so much for your time today. Really appreciate your insights into digital twins.
Thank you. Thank you for asking us to participate.
Yeah, thanks for having us.
Autoline This Week partnered with the Consulate General of Canada in Detroit to produce this episode.